Hello everyone, welcome back to Electronics 1. In this lecture I'd like to look at how we can design for a specific biasing operating point of a MOSFET to obtain a certain bias, and we use these same techniques to calculate a specific bias point given the design of a bias circuit. Okay, so I'm going to do this one from a bit of a design perspective, but again, these same techniques could be used to calculate the bias conditions as well. So I'm going to assume I have a MOSFET with a threshold voltage of 2 volts, a process transconductance parameter of 20 microamps per volt squared, a channel length of 10 micrometers, a channel width of 400 micrometers, and I want to design the system for a drain current of 0.4 milliamps and a drain voltage of 1 volt. Okay, so let me draw my circuit here. So we're going to assume, as will typically be the case, that I have a MOSFET that has the source and body permanently connected. And this particular MOSFET has a positive 5 volt supply and a negative 5 volt supply. You might recognize the naming convention used on these positive and negative supplies, common for MOSFET or FET based circuits. I've got a resistor connecting the drain to the positive supply and a resistor connecting the source to the negative supply. Okay, so I want my drain voltage here to be 1 volt. I want my drain current to be 0.4 milliamps, and I'm just going to label this is my gate to source voltage and this is my drain to source voltage. Okay, and what I'm trying to calculate is my resistor connected to the source and my resistance connected to the drain. Okay, so my first step when doing any kind of bias analysis, whether it be of a BJT or a MOSFET, is to confirm the operating region. So let's determine the operating region so we know which equations we can apply. Okay, so we might note here that the drain voltage, we said we need to be 1 volt. Since the gate is connected to ground, I could actually say that the drain to gate voltage is 1 volt, since I'm told my drain is 1 and my gate is at 0. Okay, I could express or calculate my drain to gate voltage as the voltage at the drain with respect to the source minus the voltage at the gate with respect to the source, just to get these in quantities that are going to be helpful in determining the operating region. Okay, so with that in mind, I can say, well, I know that my drain to gate voltage is 1 volt. So rearranging this equation, I can state that my drain to source voltage is equal to my gate to source voltage plus 1 volt. We know that for operation in the triode region, that my drain to source voltage is going to be below my overdrive voltage, and for operation in saturation region, we know that my drain to source voltage needs to be greater than my overdrive voltage. So here we'll note that my drain to source voltage is my gate to source voltage plus 1. So we know the threshold voltage for this, which was given up here, is plus 2 volts, and it'll be always a positive value for an N-channel enhancement mode MOSFET. So this corresponds to operation in the saturation region, right? My drain to source voltage is greater than the gate to source minus some minus 2 volts, because it's the gate to source voltage plus 1 volt. Okay, so the operating point Q is in the saturation region. Okay, so that's our first discovery. Now, what else can I calculate from here? Well, even without calculating the operating region, I could calculate this resistance of the resistor connected on my drain. I have the voltage on one side of the resistor, the voltage on the other side of the resistor, and the current through it. So using that and Ohm's law, I can calculate my resistor RD. So voltage on the top of that resistor minus the voltage on the bottom, it gives me the voltage across it, divided by the current through it, will allow me to calculate that resistance. And I find that that resistance is 10 kilo ohms. We should be careful here. Maybe I'll write this as 0.4 times 10 to the minus 3 amps. Okay, so we've got that resistor value, 10K. What else can we do here? Well, since we know it's in saturation, I know that this equation applies. I know that my drain current is equal to my process transconductance parameter divided by 2, my width divided by my length, and my gate to source voltage minus my threshold voltage squared. Okay, substituting in for each of these quantities based on what I was given here in the beginning, I know that my drain current is 0.4 milliamps. I know that my process transconductance parameter was 20 microamps, and again, let me write this out here, 20 times 10 to the minus 6 amps per volt squared divided by 2. My width is 400 micrometers. I could write this out, but I'm going to take advantage of the fact that my length is also in micrometers, so the micro part can be cancelled out, times my gate to source voltage minus my threshold voltage, which is 2 volts squared. Okay, plug all that into your calculator and we'll find that the gate to source voltage minus 2 squared, or my overdrive voltage squared, is equal to 1. Okay, square root of both sides shows that my gate to source voltage minus 2 is equal to plus or minus 1, and therefore my gate to source voltage is equal to 2 plus or minus 1, or in other words, it's equal to 3 volts or 1 volt. Okay, but how can it be both of these values? Well, it can't in this particular case, because I know my drain current is greater than 0. I know I have some drain current, And I know that my because my gate to source voltage that therefore has to be greater than my threshold voltage, right? Because again, I know my drain current, I said right here, my drain current was 0.4 milliamps. If I have drain current other than 0, then this must be true. My gate to source voltage must be higher than my threshold. I must have a channel formed under my gate. So then this can't be true. That gate to source voltage would be too small to create a channel and would result in no current. Okay, so therefore my only valid gate to source voltage is 3 volts. Okay, so I now know that my voltage here from gate to source from here is 3 volts. In order to calculate this resistor RS, it would be helpful to know what the voltage here at the source is. Since the gate is at ground, the source voltage is in fact equal to the voltage at the source with respect to the gate, or negative of the gate to source voltage. Okay, so it's equal to negative 3 volts here, right, as I go through from the gate to the source. Okay, so that gives me my voltage at the top of the source resistor. I know my voltage at the bottom of the source resistor is the power supply, the minus 5 volt power supply. So that divided by the drain current. Why the drain current? Well, because we have a MOSFET here, and MOSFET has the same current in both the drain and the source because we have no current flowing into the gate. Okay, so the drain current is equal to the source current. So I have minus 3 volts at the source, which is the negative of the gate to source voltage, minus the minus 5 volts at the negative power supply, divided by 0.4 times 10 to the minus 3 amps for a source resistance of 5 kilo ohms. Okay, so this resistance is 5 kilo ohms. So with the positive and negative power supply as shown, the gate connected to ground, and a 10K resistor connected to the drain, a 5K connected to the source, my device will operate at the desired operating point, which was a drain current of 0.4 milliamps and a drain voltage of 1 volt. Okay, often when you're looking at bias circuits for MOSFETs, you'll see that the gate and the drain are connected directly together. Okay, so you might see a MOSFET like this that has the gate tied directly to the drain. It's a really common connection. Okay, let's see what mode of operation this puts the MOSFET in. Okay, well, if we remember that in saturation, let's say recall that in saturation, the drain to source voltage has to be greater than my overdrive voltage. My overdrive voltage being my gate to source voltage minus my threshold voltage. Well, in this specific example here, my, let's see, this should be source. In this specific example, my drain to source voltage is actually equal to my gate to source voltage. Okay, so no matter what my threshold voltage is, I guess assuming a positive value, then my drain to source voltage is always going to be higher than this, than my gate to source minus my threshold. Okay, so since VT is positive for N-channel enhancement, and as soon as I see this connection, I can immediately know that my device will always be above pinch off or, in other words, it's always in saturation. Okay, so whenever you see this connection directly between the gate and the drain, we immediately, without doing any further analysis, we know that the device is in saturation. Okay, we'll use some of this bias point calculations for in the next lecture to come up with our small signal parameters and do a small signal analysis of this same circuit.